The purpose of this lab was to analyze the motion of a star of a known mass in position in orbit around a black hole of an unknown mass. Through principles such as Newton's second law of motion, the momentum principle, and Newton's law of universal gravitation, the mass of the black hole was determined to be 4.57 e to the 31st. To solve for the unknown components for object in motion, I first identified the object in motion, which was initially established as the star, then the total interactions and the total forces acting on the star in motion. For this lab, the information about the change in the position of the star in orbit of a black hole was given. From this data, I then assumed that the only interaction acting on the star was the black hole, and the only force exerted on the star was from the gravitational force the black hole has on the star. The momentum principle defines momentum as a change in velocity times the mass of a known object. From Newton's second law, I can deduce the relationship between the change in momentum of an object and the total net forces acting on the object. When an object in motion has a path that curves, its momentum is continuously changing. A change in direction, regardless of the change in speed, means that the change momentum is non-zero. And since the momentum principle shows that the change of a momentum is directly related to the net force acting on the object, I can conclude that the total net force acting on the object is continuously non-zero as well. Demonstrating this motion with a computational model, my code included three main components. The first part of my code includes the initial conditions, the mass, the imported series of positions of the star, the location of the black hole, and the time steps for over which the positions and the velocity of the star will change. The second part of my code includes a while loop that calculates the changes in velocity of the star over a time period delta t. From the known mass of the star and the known instantaneous changes in velocity of the star, using the momentum principle, I could then calculate the changes in momentum for the star at different time steps. The computational model stores this information in a list. The last part of my code pulls the changes in momentum from that list and calculates both the parallel and perpendicular components that sum to the total change in momentum. The change in momentum of the object has two components, both parallel and perpendicular. The parallel component determines the change in speed of the object, and the perpendicular component distinguishes changes in the direction of the object. In space, I assumed the only force acting on the star was from gravity, and that the parallel and perpendicular components of the momentum are affected by the parallel and perpendicular components of the gravitational force, respectively. Running my computational model, the projection of the star and changes in both the parallel and perpendicular components of the momentum demonstrate the orbit around an invisible black hole that, for this laboratory's visualization purposes, has been represented with a black circle. We can solve for the overall change in momentum from our updating function as the velocity of the star changes. We can directly solve for the parallel component that acts in the same direction in the speed the star is traveling at the instantaneous point of t. We can plug our values into the equation for the summed components of the change in momentum to solve for the perpendicular component of momentum. The red and white arrows represent the total and components of the star's change in momentum, respectively. This is also represented by the arrows in our computational model. Earlier identified the only force acting on the star and affecting its momentum was the force from gravity. Newton's law of universal gravitation concludes that for two objects of a known mass and a known distance apart, the constant of universal gravitation can be used to calculate the force of gravity exerted on one object by the other. With my model, I can conclude that the net force acting on the object as its momentum changes for a series of time frames given by delta t. I also know the constant of universal gravitation and the mass of the star and its distance away from the black hole. What I don't know is the mass of the black hole. Rearranging components of Newton's law for universal gravitation, I can solve for the mass of the black hole at different locations in the star's orbit. My computation of the mass of the black hole varies with positions of the star in orbit. Why? Because the orbit of the star is not a perfect circle. Its distance from the black hole varies, which means my calculations for the mass of the black hole also varies. The question of which calculation for the mass of the black hole stands. The average of the identified masses of the black hole is 4.57 e to the 31st and serves as my best approximation for the mass of the black hole. What if I remove the black hole of the identified mass and replace it with a new black hole? If the position of the star was the same and that of our original position and the path of its orbit did not change, could I calculate the mass of the new black hole? Using the same method from Newton's law of universal gravitation, I could solve for the mass of the new black hole and approximate it to be the same as the original. But what if when the black hole was removed, it was replaced with one of a different mass? Would there be a noticeable difference? Yes. If the mass of the black hole increased, then the increased, then the gravitational force acting on both objects by each other would increase as well. From what I know about the net forces acting on an object and how it in turn affects momentum and instantaneous change in position, the path of orbit by the star would differ from that with the original black hole. We can relate the parallel components of the change in momentum to the parallel components of the net force acting on an object. Likewise, I can do the same with the perpendicular components of the change in momentum and the perpendicular components of the force. But this does not mean that the change in momentum and the change in force are the same thing. The change in momentum measures the change in velocity for an object with a known mass. The change in velocity of an object with a known mass is directly related to the net forces acting on the object. I can remove the change in velocity from the relationship with the net forces acting on the object and the change in momentum and yield information about the changes in momentum from total net forces acting on the object. For the measurement of stars in orbit, we can use these relationships to solve for unknown properties of the system of study.